some of human manufacturing.
How much weight can you carry?
Yeah. The balance between weight and
Total, how much is the total weight?
I'll get into that as we discuss the excavation deposition. So as you can see, our main drivetrain body would be consisted of two sidebars and support beams in the middle. Our idea was to have gusset plates over here. So this is one separate component. Here is a separate component, and then the support beams in the middle. We had an idea of using gusset plates to keep these two components together, but with the restrictions that we discovered further, we're just going to screw these two pieces together. Furthermore, for the support beams, we decided to use L angles to connect this to the main body. As I said, as we had restrictions. As I mentioned before, all of them are aluminum, and the main sidebars are 35 inches long, and the support beams are 15 inches long. So the chain and sprocket system is, as I mentioned before, it's pretty. We're going to add an enclosure so that it can support so that it can stop dust from getting into any of the components and making it affect the movement of the robot. And yeah.
So do you have a working prototype of that mechanism?
show the
At the end, we bring it forward.
Yeah.
The drivetrain, it's little yeah, and we have not screwed it fully.
Yeah.
So yes or no?
Yes, we have the back.
We're waiting on for us to get the sprockets to be delivered, and once we get that in, we can start putting everything together. So as we discussed earlier, our ideal weight per wheel would be around 1.5 to 2 kilos, which can be changed depending on how much strength it can handle, the infill percentage, everything that we discussed before. And the wheel won't just be this size or that size, as we will be adding grooves on the outside for it to flow properly through the sand. Once we get our proper infill percentage and our wheel finalized, then we will be able to test how the wheel flows with these grooves on sand itself,
Something like this.
on the BP1 sand, so that we can see how the bot moves and how it goes around the.
Okay, any kind of specific reason why you have like inclined teeth built on? What?
So initially, we did decide on just straight bars like that, but I think when because it's not traditional sand, so we can't just push it. It's a little more dense. So our design was focused a bit more on how the wheel flows through the sand. We're hoping that this works. I think
another problem was that it starts sinking. We didn't want it to fully sink. So as per some of the simulation that the ME team did, this is more helpful.
Especially when it goes with the skid steering system, as you have wheels rotating on the spot. We try to come up with something that can reduce how much it sinks down when it's turning.
The things I'm worried about, if you look at the entire summary, if your teeth be in same direction, it because the new issue about your control. So if you want to have this kind of teeth, I would suggest you have V type or just W type, so that you can have like a symmetrical configuration issue instead of
Okay.
Another thing is how you define size of the wheel. What's the
Dimension.
ground to determine this size?
Diameter.
Yeah.
I can't.
I didn't understand. Sorry.
How you get the 11-inch for your size?
Oh, that's what we designed on the CAD model.
For the ground clearance.
So how you determine that? I mean,
How we determined the size?
Yeah.
That was just our initial design. As we just showed, we are experimenting with different sizes as well. So it's 11 inches is around the amount that we need, as we believe that that's enough to support the robot as well as being light enough.
We determine the diameter by the linear actuator support, how much down the excavation system can go, the bucket ladder system. So we have to have this specific amount of ground clearance for that linear actuator to go inside the sand, the excavation system to go inside the sand. That's why this is the most optimum.
And for the deposition system also, we have a flap that opens up, and we wanted certain height from where we drop the sand, and we could only control that using the size of the wheel.
Early on, sorry,
I just think that just with your like kinematic constraint, you have like space constraint for sure. Another thing I would suggest you to consider that if you relate to what kind of speed you want to have and what will be the gear ratio you want to use in your like the gear transmission.
yeah.
Then eventually it will be the power transfer into the speed, right? And it will be directly related to the size of your
Yeah.
diameter.
I think early on, when we started making our CAD model, we did do hand calculations on what would be on stress and strain calculations on how much load would be applied to each wheel, and I think we calculated from there to decide what, along with other other reasons on why we came to this size of the wheel.
Okay.
So we did like a motor sizing based on like our wheel dimensions and what wheels like what motors choose based on our thing. So we chose like a ground speed of I think 3 meters per second if I'm not wrong, and 3 meters or 3 kilometers per second.
3 meters.
3 meters per second. So 3 meters per second was the base speed which we want our robot to run, and on basis of that, like I mean, while we were doing calculations, we were just going through different like optimum wheel diameters because the wheel diameter, obviously, four wheels will affect the size of the motor which we want and everything. So we were experimenting with different wheel diameter sizes. We even checked with other teams like what size, what wheels they are using. We have like Purdue main campus's wheels to show because they graciously gave it to us so that we can do our testing and our brainstorming based on that. Although we did not use a similar design or we did not use their design, keeping that size in mind, our wheels are a bit bigger just because it's not like we are having like a as less mass as other teams are doing that team is doing, but at the same time our wheels should hold the weight of the bot which we are expecting it to hold.
So for the excavation system, as we mentioned before, we were using the bucket ladder. Our total mass as of now from the CAD simulations is 16.6 kilos. So the main aspect of our excavation system is rather than using a straight bucket ladder, we decided to add a bend and an angle so that it can help with a lot of different reasons. Which I'll mention later on. We have two belts which will be in the middle, which will be on either side, which runs the excavation system. We will be using 20 scoops, and so that we have as much sand as we can. Um, and then we also have these side plates, which will be aluminum, so that it can support not only the massive sand collected, and it also makes sure that the excavation system doesn't break down at any point.
Even like it helps with the dust mitigation because the entire excavation system will be exposed to a lot of sand. Having the plates there will support these gears and belt pulleys so that the sand does not interfere with the pulley mechanism. It is corrosive in nature. Our pulleys are like plastic, obviously, PLA plastic. So it will cause corrosion in the pulleys. So we need to make sure the dust is as least exposed to the sand as it exposed to the pulleys as it.
We are going to have a further covering on top of this as well, so that as he mentioned before, NASA has a requirement with the amount of sand that gets on the robot. They also have a requirement with how much sand gets thrown around. So how much dust is overall in the room just gets thrown about due to the motor collecting sand. So once we add the covering, all the dust that's collected will be enclosed within its own space over there, so that nothing goes out and affects the rest of it.
How do you know that mechanism works?
Um,
Have
That's
you
a tough-
simulated it?
we haven't simulated it as of yet, but from what we know, it should. I mean, our calculations for where the gears are positioned and how it moves overall was.
We have simulations. We run the simulation from the software team perspective in a software called Gazebo. Over there, they work and we run it through our perception navigation stack. I don't think ME team has done a test like how much they pick up and all, but the system as a whole works.
The
Question that I have with that is that I'm not an engineer, but I know that when you pick something up from sand, then there's less and less to pick up.
So that's why we have the radar sensor, because the radar sensor is going to measure how big of a hole it has created. For example, if it detects like it has like a 13 centimeter hole in the ground, that's when you know that okay, you can't collect enough sand, so the robot might maneuver like front or back in order to find like at least like a 2 centimeter clearance, so it knows okay that much amount of sand is present, and then it will start excavating.
Testing a system where we can match the speed of the bucket ladder and the wheels, so that when it's picking up sand, we can keep moving the rover slowly ahead, and so it doesn't just pick up in one place and keep rotating there.
Did you consider an alternating scoop location design? So instead of being straight,
we did brainstorm about that, but like if we introduce an alternating scoop, like based on what you are saying, what I'm understanding, like alternating scoops like that, so that reduces efficiency to some extent. There are like couple of teams who implemented that, but like since we have increased the size of the scoop and also like the number of scoops which we have, our the motor speed with which we are running the entire excavation system is slow, so we don't lose a lot of sand. We make sure that there is a lot of sand filled into the scoops, so that there is no percentage error in the excavation. And when since it's slow, it doesn't just throw the sand here and there, it will deposit directly into the deposition box, so there's no loss of sand even in deposition as well.
So, sorry, no, go ahead.
On the belt drive system, the two I play with 100-year-old woodworking equipment that's all belt drive, and two belts will never run together. One will always track faster than the other.
That's why we have the belt tracks, because we attach the two belts together with those tracks, and that they both move simultaneously.
That's my concern, is that you're tying together two things that don't want to run together with your scoop, right?
Right. Yeah.
So I would suggest either you have one belt system that's the full width, or you divide the scoops across the two, and don't try to put a mechanical connection between them.
Okay.
Because even really highly precisely manufactured belts will not run together. They just won't. It's just.
I mean, I think our idea was also that since we have, I mean, you might be right, but like since we have the scoops to keep it together, it might run together. But like you said, we will look into that.
There's a very destructive force there. The scoops are. You don't. That's not the purpose of the scoops.
So
Right?
even if we are using one motor to drive both the things, you're saying there will be a chance that it will fail. Good chance that it will fail. Yeah.
If you take like V-belt pulleys that have multiple slots in them, and you put three belts next to each other, they have lines on them, so you can try to time them.
Mm-hmm.
And within one revolution, they're off by an inch or two.
Okay.
So those are coming from a supplier with very high tolerances on belt lengths. I'm assuming you guys are going to make your own belts. You're going to have an 1/8 inch, 1/4 inch of variation between the two belts you make, because making belts like that is very hard.
Oh, we ordered belts from.
Continuous, or you're going to have to make the link.
Yeah.
Yeah, if you have to make the link, there's going to be enough variation that it'll be a real problem.
We'll definitely look into that.
Yeah, that's a good point to consider.
Then yeah, so we have multiple different gears placed in the excavation system, so that hopefully the belts flow properly, and well, we were guessing that it would move simultaneously. Hopefully it still will with a bigger belt, but that's why we have multiple, so that it could match the design, which I will get into. Sorry. So the reason that we decided to choose an angle design rather than a straight bucket ladder was, one, so that sand doesn't fall from a height. As we saw videos, we've seen multiple videos, and during our brainstorming sessions where we saw how other teams operated in the pit, there was dust getting thrown about was a big issue. And when we had our CAD model with just a straight bucket ladder, a lot of the time there was a lot of clearance between the bucket and the scoop itself. So we decided to go with a slight angle so that the sand could fall directly into the bucket rather than have more clearance. And have more room for the dust to just spread about in the air.
This also increases the circumference of the belt, so we have more buckets on it. When we have a straight belt, straight design, we have less buckets and it reduces the efficiency. So,
As I mentioned before, our side plates are going to be aluminum. Our max capacity per scoop is going to be 340 grams of regolith based on what we measured on the CAD model. And as we have 20 scoops overall, our estimated per cycle, we would get around 4.08 kilos of regolith per cycle. This is assuming that each scoop is filled 60%, not 100%. We're not expecting each scoop to get completely filled with every time it rotates, but so far this is our estimated. We also have further support on top of the excavation system, not only to support the system overall, but also so that we can have a LiDAR mount, so that we have a place where it's big enough to look at the entire map and also send and also sorry. So that it could be supported properly on top of the robot and get a proper view of the entire map.
Yeah, we need to make sure that the lidar is not in direct contact of the sand, or like it will definitely have a lot of dust on it, but we need to make sure that the lidar is placed in such a way that it doesn't move at all during the entire cycle. If it moves, the entire calibration set by the software team fails or has a chance of failing. That's a failure mode again, and we won't be able to run on a fully autonomous mode until we recalibrate the sensor.
And since I mentioned that we would be adding a cover for the excavation, hopefully none of the sand would actually get on or in front of the lidar, or not much sand would get in front of the lidar to mess up with any of it. So for our deposition system, we have it's the storage capacity of about 0.05 meters cube, and it can support around 45 to 50 kilos of regolith, which works perfectly with how much we theoretically would want. The deposition system, as I mentioned before, it's going to tilt forward and sand flows down. As a slope is just the easiest way for us to get sand down. And the vibration, as we mentioned before, for sand to flow freely out of the bucket. So in our buckets, we added these 4 ribs, not only to help sand flow, but also to support the bucket itself so that it doesn't collapse when we have a large amount of regolith on the inside. For further helping with sand not escaping from the bucket, we are adding a door on the outside of the bucket, which will be operated using servo motors. It's not going to be something that not strong servo motors, just something that does the basic function of making sure that it's closed fully so that sand doesn't come out, and opens when we need to deposit sand into the deposition zone. Then on top of this area of the deposition box, we will be placing our electrical components. And in our electrical components box, we are adding a small little cover so that sand doesn't fall into the electrical components area, and so that it's guided directly into the bucket. I think we can move on to the AC.
So just one thing to add: the door mechanism works in a way like how container trucks have that back door which just lands downwards, creating a slope, and you can just move everything using a cart. That's exactly the same principle, but at an angle. So we don't have a cart; it just slides down using friction. I think so. Okay. So for our electrical architecture, like I mentioned in the system boundary diagram before, our entirety of the robot is controlled by batteries and electricity. So that's where the electrical team comes into play. So like I mentioned before, we have a power distribution board which is basically connected to every single component on the robotic system. And then we had initially planned of using cameras. We should be having cameras on the thing, but we won't be using it because if we switch on the camera, we tend to lose a certain amount of points which we cannot afford to lose at this point. Eunice. Oh, you can.
Okay, so for powering system, we have four this 6L LiPo batteries, four in parallel as you see, and then we have a BMS board for charging it, and then we have to have a 40 millimeter in diameter e-stop button. So as seen in the previous slide, so that's in series before the PDB, the power distribution board, and we also have the data logger, which has a LCD display on it, and it has to be off the shelf by the requirements. So then there's the power distribution board. So there's two sections to this. So there is the 5 volt and 3.3, and then thereafter it is to the motor drivers. But as for the 5 volt system, this is to power the Jetson and several other Jetson or any microcontrollers. And then we decided to go with this particular IC because it was used in a lot of other RC related projects, and it's very reliable, it's very proven, very simple. So I think that's what we should be going for. And then we have then fuses for redundancy, and then just simply an LED to show that it's on. So then the next, and then the next one is very similar, but this one is for the 3.3 volt system. And so effectively same thing, but the V out is 3.3 volts instead of 5. And so this is the current PCB. Right now, we are reducing the size of it because it's a little messy, but it's functional. And through the simulations in Altium. And so this has both circuits and has all of the software fuses, some of which are not necessary. However, keep them, doesn't hurt, and use the fuses and maps like that. And it's for redundancy, as I said earlier. And then this is the input. So and to the side here, we can, without soldering it, we can just unplug or plug back in, mainly for the use of charging the batteries. And then
so we have to control the motors, we'll be using the TNC 4.1. One of the reasons why we chose this is because we're gonna go over the main microcontroller later, but that's already has all the processing power, and so we need something that's lightweight in terms of processing and just gives simple command and has enough PWM ports, which is the method we're going to be using to control the motors and its speed. There were two options. There's the Raspberry Pi Pico, which has about 14 pins of PWM, and then the TNC 4.1, which has 28. Really, we realistically only need 8 at most. But the reason why we chose the TNC over the other microcontrollers was because this has faster communication with the Jetson Nano, and in terms of being able to process some of the commands it's going to get from the Jetson Nano, it's able to do it faster than the Pico. So what it'll be doing is it's going to be getting a vector, and using that vector, the TNC will be the one deciding how to convert that into PWM signals, and thus determining what speed to go at, in which direction for how long. And the TNC connects to a motor driver. Why we have the drivers is because the TNC itself can output a maximum of 5 volts, and the motors need 12 volts.
12 volts.
So this is why we need a motor driver, which will be in between to interpret the PWM signals and essentially convert the 5-volt signals into 12-volt.
Yeah.
And specifically why we're using the Sabertooth is because honestly, I've used it before. It's reliable. It doesn't heat up as much, and it also is relatively inexpensive compared to other motor drivers. There's also a size thing too, because compared to other motor drivers on the market, it is much smaller footprint in the um, like electrical box we're gonna have on the bot. And then uh, uh, we also for the um, sensor wise, we're gonna have UWB positioning to go alongside the navigation and perception. The reason we have UWB is because there's limitations on how we could localize a position on the field or the map. Um, One of the rules is that we're not allowed to sense the walls. So we can use that for localization. And if we assume that we're in a big barren land, how do we figure out our local position? So we are allowed to have anchors on the field. Unfortunately, it's limited to the starting zone. So the starting zone is 2 meter by 2 meter. And the blue spots are the anchors. Anchors are basically the sensors that don't move, and then tags are going to be the sensors that are going to be on the bot that are moving. So the blue ones are anchors, and we're going to put them in a triangular formation to do triangulation of the bot. The reason we have two tags on the robot itself is because one of the rules says is that we don't know which position we're put in when put in the field. So they can rotate it towards the ball, they can rotate it towards the arena, who knows. So to calibrate it, we are able to tell the front and the back of the bot by using two tags. So that way it'll be able to turn according to wherever it determines is the excavation zone. So there are these sensor could have been anything, but why we specifically chose UWB is because if you do a light-based sensor, that requires line of sight. Unfortunately, there is a pillar in the middle of the field that will break line of sight with the bot if we ever pass it. So we need something that can communicate around those pillars. So that's why we chose UWB. Because it doesn't require line of sight, it has a great range, and on top of that, it doesn't necessarily interfere within Wi-Fi's frequency, which is 2.4 gigahertz or 5 gigahertz. So that's where UWB, which can go up to 8.3 gigahertz, will be um, uh, better to use because again it doesn't interfere with the Wi-Fi signals, because there's this rule: if a Wi-Fi connection ever breaks with the bot, we stop the run, and we have to we disqualified. Is it disqualification for yeah it is yeah. So that's why we want to play everything safe, and we did find a board. um, the Arduino Stella, it is a much newer board. It came out in 2023. So it is, um, again, pretty new. There isn't enough information about it, but uh, it is worth the fact that there aren't that many libraries, purely because of the fact that the chip it uses is the TrueSense DCU40, which is better than the Qorvo DWM 1000 and DWM 3000. So that's one of the reasons why we chose this board. On top of that, um, it's much smaller than any other UWB board on the market, and also it's very low power. It runs on a coin battery, and like any other boards which would require 5 volts power supply.
Like we said, for the software and all the decision making, and as a GPU on board, we use Jetson. It's by NVIDIA. It's called the Jetson Oran Nano. It has a good computational power, and it doesn't take that much of the battery usage also.
So right now we are having problem with the RAM when we are using the ATCS computers, and now we are shifting to the Jetson when we are testing it. So it has a good RAM which will have a good FPS and everything.
Now, finally, starting with the software stack, we'll do it quickly so we don't bore you guys more. Uh,
So this is the software architecture overview top to bottom. At the start, we have the Unitary 4D LiDAR L2, and it feeds its data into two stacks which runs simultaneously. The perception, which detects the obstacles in the bit, and the localization, which tells us where the robot is currently. These two forks its data into the nav2 pipeline, which decides where the robot has to go, like what path it has to follow, and it basically decides where the robot should traverse. And then it gives the data to the behavior tree, which is the brain of the robot, and it tells the robot, okay, now it has reached the excavation zone, you have to dig, and when it has reached the deposition zone, now you have to deposit the sand. And in turn, that behavior tree gives the data to the hardware, which then converts it into the command velocity and runs the robot at that specific velocity. Simultaneously, we have the safety monitor, which is the independent e-stop button, and it does all the safety checks, and it stops the robot at any point if it fails any of the checks. And the adaptive tuner is basically the velocities at which the robot runs, depending on the amount of weight it has picked up or something. So this is this.
So one of the main concerns in this kind of environment is that the ground is never plain. You have rocks and you have craters. How do we detect this with a single sensor like a LiDAR? Luckily, the LiDAR we have is a 4D LiDAR, and it has a good scope also. Like we said, it's 360 into the 96 degrees and 64 points per second. So what we decided to do is, let's say this is the crater. We get the point mesh of the crater and we invert it, and we think of it as a rock. So the rover will know that it should avoid this also. We hold some kind of a margin that okay, this much radius you should leave, and then move and think of your path around it.
So basically, it takes the raw LiDAR data and it crops it to the region of interest, which is approximately 4 meters ahead of the robot. And then it does ground segmentation where we know exactly where the ground is. And after we do that, we classify the objects above the ground, 10 centimeters above the ground as a rock, and 8 centimeters below the ground as a crater. And then we invert the craters as Amit spoke about. And based on that, we do the perception stack and detect all the obstacles in the pit.
Basically, craters and rocks would be handled in a similar way, like the traversing around them, so that we don't have to handle them individually in separate ways.
Two main reasons of not using a camera is other teams like Purdue West Lafayette, they use a camera and then they do a image segmentation. They try to identify this is a rock, this is a crater, this is a beam. But we think it's not necessary. You have to avoid it anyways, and we also lose points when we use a camera. And our Jetson can't handle so much of computation of LiDAR, camera feed, running a YOLO model to detect images. So we avoided all that.
So you're in the Waymo camp.
Yeah,
You're in the Waymo camp.
Yeah.
we have a bandwidth limitation. So that's it. So this is the localization where it tells us where the robot is exactly at each point. We'll run 3 layers, and basically our point of running 3 layers is that even if one fails, we have the other two, or whatever fails, we have at least one layer. The first layer is the point LIO, which basically makes a cost map based on the data coming from the LiDAR. The second one is basically taking data from the encoders on the wheels, and it combines it with the IMU to give us how much the wheels have turned, or what angle it is, if it is in a depression created by the digging. And the third layer is by the UWB anchors, which is basically there are GPS beacons which we place at 3 ends of the pit. It basically creates a triangle and it gives us distance from each of the beacon, which helps us to plan like where is the robot exactly at.
And like we said, as a human, if I've seen this place, I don't really need to see it again to know I have to avoid it. So we create a cost map on which when it's moving through the field, it says, okay, in this block there's a crater, in this block there's a rock. So it doesn't really have to see it again compute it. It has a virtual plan of it.
Yeah, the point cloud data essentially maps to the cost map, and then a cost map is created so that it never has to.
Are you saying cost map or course map?
Cost
Cost
map.
So why is it called a cost map?
So cost map is basically it is a top overview of the pit, and it has basically a lot of grids. Each grid is marked as a safe, obstacle layer, or like unknown. So basically, we do the cost map divided into 4 layers. The static layer is basically from the point cloud, the lidar data, and the obstacle layer is basically where the obstacles are, and we have to like avoid it. The inflation layer is the buffer layer around the obstacles, and we take it as 15 centimeters around the obstacles where we shouldn't go near it. And the keep out layer is basically from the arena boundary walls.
Essentially, like speaking in like general terms, if you know what a heuristic is, like it tells you the cost. Oh, can you go there? Can you not go there? Something like that.
And
So
this
it's
name is,
predicting which area
yes,
to go
and
to.
this name is given by the ROS, the robot operating system. They have their own packages. They itself call it cost map.
Yeah, and in the first slide we spoke about adaptive tuner. You must be thinking what it is. It is basically what velocity the speed which the robot should move based on the localization quality or based on the amount of sand we have picked, so it shouldn't slip.
So the idea is that we have everything hard coded. Then what is the smartness in the robot? How is it really autonomous? But we cannot give it full control. So we have a banded control we give. Okay, you can go from this velocity to this velocity. It decides that on how much sand it has, how much time it has left. It will after each run, it will recompute its last run, think how it did, and then it will plan the next run better.
For the excavation also, you can see that the motor current exceeds this limit. It will the duration for which we dig is this much, and so it basically we have set.
It's pretty like self-learning almost, but at the same time, creating something like a Tesla car is going to be pretty hard. So for the most part, it is autonomous for NASA standards.
And no other school, yeah.
Is that possible the robot make the entire room in the quick?
Yeah, so
The way we handle craters are the lidar gives a certain range of data, and we also accept only a certain radius. So it can't really see beyond a point and think of the whole room as a crater.
this question is we take that also might get a dictator, but we what we do is when we start, we take a whole scan, and before starting digging the first time, we know where the craters are. So even if we dig, we know like craters can't be created by like from the starting. So we know if
And
the crater is there.
Either way, we have
the UCF map and the Kennedy Space Map, they've already given the dimensions of the map. So the robot already knows how big the arena is. It plans it accordingly.
And there is an obstacle zone before the excavation zone. So there will be we know where the obstacles will be.
Correct.
Next.
So this is one of the main important things. We call it's called behavior tree. There are it goes in sequence. First, it will understand where it is. Then it will do a path planning, and then it will tell the ROS. It will publish it's okay. We are here. We can move forward in this speed in this direction. Once it does that, it will again go back again to that process and compute its next steps.
So for we localize and then we navigate the path, like we plan where what path we have to follow. Then we go to the excavation zone. We excavate. We traverse the obstacles again after excavation and take a scan. Then we go to the dumping zone and we dump at the berm. Then we relocalize again and then we follow the first 5 steps again. So this is basically the brain of the robot telling it what to do.
So after each cycle is done, it publishes, okay, it was a status, it was a failure, and on that it will decide what it has to do next. If it was a failure at excavation, it will decide should I move somewhere else and re-excavate, or should I continue with the amount of sand I have and go and deposit.
And is a failure, how is a failure defined?
We'll set ranges that how much sand we have picked up and how much time we have spent doing this. And if after 3 tries or 4 tries, If the robot still thinks it's not able to do, it will tell the operator, and then we'll do a semi-autonomous cycle for that run.
There's a DFEMA slide coming up where we define where how
Yeah,
the
we
field.
have a few TPMs.
And also the two sequence. This is the most important parts where we do the safety check after each cycle, where we do the how if the communications are working, the sensor is working, the battery is working. If it's not working, we stop no matter what we are doing and we go to semi-autonomous. And this is the perception layer where we check if the localization is working and the lidar is working.
So does that mean that if you have like a human inconvenience, you lose points for full automation?
Yes.
Yeah, so fully autonomous is basically 600 points where we have to do at least one cycle.
No, 2 cycles.
2 cycles completely autonomously.
They think of autonomous very differently. They think of it as from picking up sand to dumping sand. They call it as a cycle. So if that much part we do, 2 of those runs we do autonomously, we get those 600 points.
Essentially, if we start, go to the excavation zone, drop off, and then again start. And then
Fully autonomous means no intervention from humans, zero intervention.
So how would they know that it's a excavation site and the
We have
stopping site?
we
You
have a
have to tell
sequence
them
plan.
initially. Okay.
We should have put a photo of the map, but they have already given the 2 maps that are going to be there.
yeah,
And we already tell the robot that this map is going to look something like this. Initially when the robot is put, it will be in it will face any direction. Using the UWB, it will know, okay, I'm facing here. The excavation is there, dumping is there, and as it starts moving, it starts creating a cost map. Okay, there is a rock, there is a beam. It has a basic idea, and it's also brings in new information.
Yeah, another thing that's like the basic you have like an adapted parameter. Is that automatically adapted or
Like we said in the
human
previous
adapted?
part, the adaptive tuner, sorry, these ones. So we see how the previous cycle was, how much velocity we were going with, and how much sand we picked up. It will decide if that was correct, or should we change velocity, should we change the speed at which we are picking up sand, and then it will adapt those weights for each of those sequences.
We will have code for several situations. If checks and like what should we do if this happens, what should we do if this happens.
Is that like an expert system, just like it's a roles you specify?
it's essentially a feedback loop. So
It's more like a reinforcement learning group, which we are trying to do. We cannot give it full control to think by itself, so we give it in a banded situation. That okay, if you want to increase speed, you can only increase it this much. If you want to reduce speed, you can only reduce it this much.
And it's not only for speed, everything, it learns everything from the first cycle. So we believe in simulation and learning from that. So while we were simulating, we have a screenshot of our exact CAD design in the pit, and this is the exact pit which is given in the UCF map, and we have simulated that. Here is the rocks and craters which we have created, and this is the like the deposition zone, excavation and deposition zone, which we have to cross from the obstacle zone, and these are the berm target areas where we have to deposit sand.
So right now this is in the Gazebo software, but there's one more software in which we work. It's called NVIDIA Isaac. What it does is once we put the robot inside, it keeps doing multiple simulation, multiple cycle, multiple edge cases, and it learns from those. So when we go in the real world, we already know what to do when we face certain kind of problems. And since the robot is not ready, we didn't want to waste time, so we decided that we'll do as much simulations as we can and learn from those. So we'll be
Yeah,
prepared.
but like from the map we are given right now, only one thing is will be changing, that the number of rocks or craters, there can be different number of rocks or craters there. So we are planning many simulation like easy, medium, or hard, and we increase the number of rocks and craters so that it becomes harder for the robot in the simulation.
So maybe not a nice question, but have you simulated like mechanical failures or
We
problems with the mechanism?
as a software team in the software we can't do those. It can only run the code we have written, the perception stack and navigation stack. It's not really how much sand it's picking up, and
What happens if a wheel breaks out in the middle?
that's
Or a sprocket or a drive.
very realistically, if a wheel breaks in the middle of the cycle,
I
we
don't
are
think
doomed.
that-
We can basically handle what we have to tell the robot is the brain of the robot. We have to tell whatever it has to do next and what path it has to follow. We can't do anything if the wheel breaks because in
As a
the
software team, that is not in our
I
scope
think
when we
there
run
are
simulations.
there are some things that ECE relays to us if there's any failures as well. I think that's that. It's more about like what the robot where the robot should go or what it should do rather than how it should do it.
We can do our best to decide what the robot does next and how it does. And yeah.
These are some of the technical like TPMs which we decided it should manage.
So basically, the LiDAR takes, as we spoke about, it takes 64,000 points per second and then compresses it to 6,400 points because we cannot handle so many like so much data, and it will take a lot of bandwidth. And from that 64,000 points, it does ground segmentation and it merges the obstacles with it, and then we publish it to like at 8 hertz frequency to the nav2 stack. And according to the bandwidth budget, it is a very good thing for us if as we are not using any camera and that there's zero video bandwidth. That's why we are using very less bandwidth, and that should not be a concern for us.
We are allowed total of 5 Mbps. Right now, with our calculations and simulations we have run, we only use around 165 kbps.
Because the
Then you
main
don't have a camera.
main thing is the camera bandwidth, which is
West
not.
Stafford has 5 cameras on their robot.
And also we have a camera on the robot for the fully autonomous part, sorry, fully manual part when we that is a failure mode, but for fully autonomous we will not switch on the camera.
So that's just for communication. You don't have like budget for computing.
No, this is communication only. For computation, we have as much as we want.
Yeah, it's only
You don't
for
have limits about
No, not from NASA, but from the GPU we have.
That GPU might overheat
Oh,
or
okay.
something.
I thought that you have to do everything in real time.
Yeah.
It
Yes.
is huge amount of computation. So
No, this much the Orion Nano can handle. It can run multiple local LLMs also, so it is very powerful at inference.
So we think about it like this: if we have a lot of compute, like if we do it, if the code is very complex, it will have low latency, like it will have high latency. It will do things very slowly.
okay.
By the way, considering time, do you have like a restriction on the time, or they can as much time as you need?
20 minutes, no,
30
plus 30 minutes.
One cycle is 30.
but again
In
I
that
think
once, in that 30 minutes, how many runs we do and how much sand we pick up is our goal.
yeah.
Like,
For you, 30 minutes is good enough.
I mean, that is way more than we can do because the batteries, we only have 2 batteries and it should do so much. 4 batteries, sorry. Yeah, these are some of the DFMEs and risk assessment.
So will it run for 30 minutes?
Yes.
Yeah.
Our goal is for it to run for 2 cycles, so around an hour.
With
Yeah.
4
With
batteries.
current, it should be able to run for 1 hour, so 30 minutes easily. Even if with some margin of error, if it falls down to 40-45 minutes, we still
If one
cover.
battery is not working, then we have backup.
I think yeah, we switch to
So this is the DFEMA is the standard procedure how we make the DFEMA. S is the severity, O is the occurrence, and D is the detectability. And the most severe thing is the localization rate, because if we don't know where the robot is currently, we won't be able to perform any tasks. And the second is the robot stuck in obstacles, where obviously if it's surrounded by obstacles, then we don't know. And these are some of the more severe things. The most rare occurrence is the LiDAR failure. Although it has a 10 severity, but it is very rare, so it will have the lowest points.
And when we say localization drift, it's in a sand. We think it will keep moving in this direction, but it might slip because of a crater or something. The robot is thinking, okay, I'm on this path, but it might not actually be. It might be off by 5 centimeters here and there. Moving forward, there are 3 modes in which we can operate. Fully autonomy, where we get the highest number of points, 600. If we go one level down because of some problems, semi-autonomy, we lose points on certain aspects. And then the lowest is manual mode, where some operator from the operating room will be controlling the robot using remote control.
From what we've seen, not a lot of teams aim for full autonomy
Yeah.
for some weird reason, I guess. At least the last year. But it looks like most people go for the manual teleop. I don't know. We don't understand why.
Also because this is the first season where it has fully autonomy has so many points.
Yeah.
So would you mind backing up to the FMEA?
Yeah.
So would it be important to consider mechanical failure and how you address that?
Those
So
actually
go back
DFMEs,
to
yeah. Those
like
actually,
going back to base, or having some sort of escape routine that you would make.
For the mechanical failure,
Yeah, so if you detect a mechanical failure, what does the device do?
if we detect a mechanical failure, then we have to switch to fully autonomy.
No, no,
Like
I would
fully,
challenge
that we
you
should have.
not to do that.
yeah. So the mechanical DFEM is
Those should have been included in the mechanical sections. These are
till the
No pointing fingers.
Yeah, I mean, I just think it's an important consideration.
we agree.
Yes.
Okay.
actually while we
Could you create a code like well, I saw that you have error codes. Like, is there you sense a code or have an error code of any kind of failure that is out of the scope of things that you have already programmed, and based on that, you can just decide something to do just to get out of the situation.
Exactly.
Is that what you need?
That's the idea.
Even if you do not have to classify the error, but it's just if something that is unexpected happened, like one of the wheels have broken, you just need to think about
Manage the situation.
what you're gonna do. It's like an exception.
Okay.
yeah.
How you can
I think we
handle
have.
it.
We'll look into that and
Even
we'll
if
try
you're
to add
gonna
it.
pass it to some other system to handle it, it's just you do not. The brain does not just have to.
Yeah,
read
that's a good
and
point.
clean up.
Because the brain has to decide what to do next, and yeah. And we will add that in the
That's
DFEM.
kind of a systems engineering look.
Yeah,
Yeah.
good point.
Thank you for this.
Good.
I think, yeah, Saideep, you that was most of it from the software and all the technical side.
We are tracked to deliver it as soon as.
Don't forget Dean Adelov too. So.
I mean, we considered you and Dr. Adilov in EEE Innovation Lab because it is under Dover School of
I
Business.
didn't know we were up to that much.
So,
Deep, you're quite the salesperson.
So our primary sponsors, our first sponsor for the project was Phil Wright, who graciously gave us $1,000. Then we had the dean of EDCS, who after the first system design review gave us $1,000. Then we had honors program give honor scholarships to all the honor students who are a part of the project, which came out to be 2,118. Then IEEE 428 through Dr. Grouping Wong and Dr. Zooming B, we secured a $614 of funding. EC department and CS department gave almost $500 each, and EEE Innovation Lab through Dr. David Cochran and Dr. Adilov, we secured almost $2,200, which includes the pit which they are building for us so that we can test our robot, and also majority of the electrical components and a lot of 3D prints which we have done for the past couple of days. So our total support exceeds almost 7,900, which is almost $8,000. So we in with wholeheartedness we thank all of the sponsors for all the support they have shown. This is the first time we are presenting. This is the first time we are participating. Even before even before the submitting the proposal, we were not sure where the funding is going to come from. If people are actually going to believe that we will be competing or we will actually get selected. But when we got selected, that's when a lot of people believed in us and joined us in this journey.
You also have student travel coming.
Yeah, I was coming to that. Then our upcoming milestones. Next week we have the systems engineering paper due, which has a specific dedicated award of I think $2,000 for the best systems engineering paper. Then on April 30th we have a proof of life. We have to submit a proof of life video.
That's
it has
Thursday.
Yes, it is this Thursday.
Thursday live.
Yes, and
We have someone working on the system engineering. It's not that we'll start it now.
I think you mentioned about the proof of life.
No, it's just saying that's very close, right?
Yeah.
Yes.
Yes.
Do you want some feedback on that?
Yes, definitely. Yeah, by this weekend we should be able to share it with you the first draft, and based on that we can make some changes until the last day of submission. Proof of life, which coincides with EC Senior Design final presentation, is on April 30th. Same day we have the robot data specifications report due, where we have the entire robot breakdown, where how we have to show how what each component does with what measures, what is the exact dimensions of every part on the robot, And on May 6th is we present the list of students and faculties who are attending the competition. And 9th of May is when we finally depart. First batch of students depart for the competition.
So proof of life means it's working.
Yes, we need to show it in the pit
And
that
what's
it's
the
working.
date for that?
30th April
All right.
is the same day as our final presentation.
When it rains, it pours, right?
Then our competition schedule is 12th of May. It starts on 12th of May and it roughly ends on 21st and 22nd of May. It's basically 12th of May is when they will have practice runs, and slowly every day they will have competition runs. Each team gets two runs to perform in the qualifiers, so that after first run they can make some changes and perform the second run.
So
No, that's not first come first serve. Practice runs are first come first. I'm not talking about practice runs. So competition after the competition runs, they will select top 10 teams who have qualified, who have outperformed other teams, and in a week's time they will like participate in the final run, which is on 28th and 21st of May. Then, with concluding the presentation, we would like to extend our special thanks to Dr. Yanfi Liu, who agreed to be our official faculty advisor. We just like first we asked her, and then she was readily she readily accepted. Then Dr. David Cochran, who has been our sponsor and mentor throughout the project. Mr. John Haverstock, who is our Philride coordinator. College of Engineering, Technology and Computer Science, and Dr. Sharif Al-Fayumi, who has also been a part of this journey. Department of Electrical and Computer Engineering, and Dr. Wong, who is the chair of the department. Department of Computer Science, whose chair is Dr. Adolfo Coronado. IEEE Fort Wayne, special thanks to Dr. Wuping Wong and Dr. Zooming B. Dormer School of Business, again, a special thanks to Dr. Adilo for all the support they have given us. It's like until the end, we didn't know like where our project was going, how we were going to test it. We were trying to make arrangements to go to a local volleyball court or something to test it in their pit. But thanks to Dr. Adilo, we are able to have a custom and fully PFW in-house built pit in Dormer School of Business. And then Dr. Amal Khalifa, who has been a big support to our CS team, Dr. Antian Wong and Dr. Elizabeth Thompson, who have helped the EC students with their feedback after each review session. Then Tech Ventures requires a a membership fee, but the president of the Tech Ventures, the facility allowed us to use their space for free of charge because it's a student-led project. Then PFW Student Government Student Travel Fund, who graciously gave us $5,100 for our travel. Then PFW Honors Program, who helped us with our additional costs through their scholarships. And Jason Moyer, who helped our mechanical team get an insight of the designs which they're building. Thank you.
Thank you. So what do you guys consider to be the biggest risk right now?
The biggest risk would be that like uh, facing manufacturing and fabrication delays and miscalculations, because if our drivetrain or the entire mechanical subsystem fails, even if we have a strong autonomy, it will not be as
The biggest point right now is the mechanical team. There are only two people who mainly contribute to it. We are not able to find more people who want to help us on the mechanical side. So that's why we are.
We did reach out to the department, but they were like, you reached out to us multiple times, but none of the students showed any interest or like they want to do it. That's why we have only two of them work on it the entire time.
All will be helping with the manufacturing.
Yeah, right now.
I think you're right.
Yeah.
Yeah, last time you use like rows to count the whole system.
Yeah.
Do you guys like how like simulation to see how it looks like when you do the count?
Yes. Right now I don't have it with me.
The ROS to the software side simulation.
Yeah. How you?
So we do it on a software called Vertigo, which we have to like.
Thank you. Yes.
Like,
Thank you so much for
we running right now.
Okay.
Focus on the computers there, and that's where we.
Sorry, it went beyond the time scope which is planned.
That
It gets a little boring in between.
but we are now shifting it to Jetson Nano OS That we will be present throughout the bit. Because it has more memory power and
I thought in ROS we are able to integrate the the dynamics like a dynamic
Just some syntax
mechanical
notes on the
axis
decom.
side. Okay. The expedition, yeah. So that's
Then just some
yeah,
random notes, and then it's about the
okay.
software piece.
Okay.
I think you've identified it.
Okay.
Anyway, I emailed it to you.
So
Yeah, you can, no, I emailed it.
we shift to the Jetson.
Yes, you I can, I check, you know.
I think that's Thank you. I mean, the main purpose of doing the review is going to you guys because
The thing is, we are doing it for the first time.
Joe is very good at applications.
Yeah.
Get these guys in here.
yeah, I was
Especially
based on his
here.
availability as well.
I have a lot of confidence, by the way,